how to connect your AD converters. If you have a bunch of digital wires falling out of an AD converter, how do you connect this to a computer? Do you have a solid feeling, understanding of this process? How do you connect 8 bits or 20 bits falls out of your AD converter to an actual computer system? Any questions on that? Come on, you have to get your head around this. So if you're not feeling confident about this one, please just speak up and say so. You have to get this whole story straight from physical phenomena all the way to complex digital systems. And it's an important step in between. Okay, so this was an example how you could connect that one, understanding that before you can use that from your CPU, you need to have another controller in between, which is connecting with the bus interface with your CPU bus. You have to have some entity which communicates with your CPU bus to do that. The synchronization has to happen. At this point, the local devices become almost always semi-active. They can do things on their own. As we saw here, we could leave jobs like convert this so and so often, tell me when something runs over, tell me when something is out of bounds, but otherwise do your own thing, no, don't disturb me at all. You can express things like this on these devices. You don't have to constantly communicate actively to the outside world. Right? So far that all feels okay and familiar? Good. Okay, those were just examples for the whole thing, which you see in your actual programs in your exercise when you go to the hardware part of the course here. So the next abstraction level is a microcontroller. What's a microcontroller? How would you define a microcontroller? Gut feeling? Any idea? Ever seen one?
It's like a whole system on a single chip.
System on a chip. That's well, and some of these things are actually calling themselves system on a chip. What does this entail? What do you find now on a chip? Systems, yeah. What kind of systems?
Processor and memory and other peripherals.
Processor and memory. And what else do you find on a microcontroller? It's also memory, yeah. Some other forms of memory.
Timers and that sort of thing.
Timers. Okay, what are timers? Why are timers so special? Do you know what a timer is? Do you know how to use them? Okay. Anybody knows what a timer is? This is again what you use it for, but what is it? This is again what you use it for. You use it to generate interrupts. What is it technically? I give you a bunch of logic, a bunch of electronics. You go to your VHDL programming environment, give me a timer. What do you do? It's a counter. Yeah. It's an independently clocked counter, which runs independent of your main CPU. You can set it to something, and it can do something if a certain count has been reached. And as you can calculate the time which this will take based on the clock of this thing and the value which is set under, these things are then called timers, or sometimes referred to as hardware timers, as opposed to what you emulate in software in your programs. A hardware timer is something you set and forget, and then it does something for you at some point. Not necessarily for the CPU, can also trigger other parts of your system. So we have a CPU, different forms of memory, and a timer. And? Input and output pins. Yeah, how many do you want? Lots of pins, input and output pins. What can you do with these in and output pins? Well, put something in and out, yeah. What electrical options, what electrical parameters do you control on these pins?
The basic,
Yeah.
the basic ones you can just set them to 0 or 1.
Yep.
Or you can read the value
Mm-hmm.
0 or 1.
Yeah. Okay. We'll have to look into that a bit more carefully. There's a lot more switches and options around these I/O pins. For example, if you want to use these I/O pins to connect your device to a CPU bus, this is not quite yet cutting it. Because in your CPU bus, you need to be able to listen to what is going on there, or to put something on there. And this is not just actively controlling that. You need to control, is that a pull-up connection, a pull-down connection, a free-floating connection? Is it a connection which is quantized? Is it a connection where you actually want to read the analog value which comes in? Lots of parameters which are around that one. Okay. CPU, memories, timers, I/O pins.
Communication hardware,
Communication hardware? What do you mean by that?
like I2C controls and that sort of thing.
Mm-hmm. I2C controllers? Okay. Anybody knows what I2C is? One. Okay. Other controllers which you heard of? SPI? Sure. We'll talk about all of these in some more detail. Okay. Communication controllers. What else?
Multiplexers.
Multiplexers. What's a multiplexer?
It's for routing signals within the chip.
Yeah, so it's more of an internal thing to connect different devices. You have a bunch of devices and a bunch of other devices, and you want to connect them in interesting ways. Often this is part, for example, of the interrupt management. Which of these devices is supposed to be able to trigger what kind of interrupt to connect with what kind of device and trigger what kind of effect. Lots of possibilities to switch that in a clever way. That's it? You have your microcontroller? Yeah, I think we have about the microcontroller from the early 80s. Not bad, not a bad stuff.
You're going to need some sort of clock source.
Clock source? What's a clock source? Is that part of the microcontroller? How do you generate a clock? Some sort of crystal. Exactly. How big is your crystal? Or you can show it with your fingers, so it must be millimeters, right? Stuff which is in the dimension of millimeters usually doesn't go on chips. Right? So your crystal is the one bulky elephant in the room, which you cannot possibly put on the chip itself because it's just many orders of magnitude larger than anything else which you have on that thing. So what you actually have is the crystal is the only thing which is outside of it. So that's the only thing which is actually wrong. This is not part of the microcontroller. This has to be outside of it. Okay. Anything else you want to put in this microcontroller to move into 21st century? Wireless stuff?
I'm thinking about wireless stuff.
Okay. You want to have an antenna on it? No antenna. Isn't that just another form of communication protocol, which you said communication devices, I2C, SPI, and you want to have now Bluetooth and... okay.
FM radio.
And radio, yeah. You will actually have chips which are built around that. The chip is basically an antenna, and you build into this antenna, or underneath this antenna, the rest of the microcontroller. This is an interesting concept about scale, because the crystal, an antenna, those are the things which are unbelievably bulky, because an antenna still has to go with actually the radio frequency. If you have a bipole antenna, it has to be some relation to the frequency which we want to deal with that one. You cannot miniaturize that any further. And so you do have, indeed, microcontrollers. I just bought one last week, which has a Bluetooth antenna on top of it. And the whole microcontroller is stuffed underneath this antenna to actually drive this whole thing, including the Bluetooth interface and the device drivers, and of course the CPU. I mean, the CPU is the tiniest part of the whole thing. So yes, not a bad idea. Okay, but those are a bit exotic microcontrollers because they are obviously built particularly to ultimately be used as a Bluetooth device of some sort. Accelerometers? Oh, that's a hard one. Accelerometers on the microcontroller? Okay, how do you build accelerometers? Okay, carve stone and suspend it with some springs somewhere, and then measure how the stone is actually moving with the springs around it. You think there's a small stone version of that? Smaller springs? Yeah. Yeah. This is actually how these things work. Smaller stones, smaller springs. If you make it small enough, these smaller stones turn into, for example, piezo crystals, and they're suspended by touching other crystals, and they're just getting in an oscillation. And depending on the pressure which you have on different surfaces, the frequencies which you get out of your piezo crystals will change a little bit. And you can then measure acceleration or gyroscopic effects if you carve that thing right. So if you carve this thing into a triangle, for example, then you see that the rotation force of this triangle will produce different forces on the different surfaces of this triangle, and you have your gyroscope. Yes. Still, commonly they are not on the same die because they are still a little chunky to be part of the microcontroller itself. Good idea. Oh, that's a clever one. Pre-written software. So you want to have the software which works already in the firmware of this whole thing, so you don't have to write it yourself.
Can it run Linux?
Can it run Linux? Well, can't you run Linux anywhere? Okay. Yeah. Pulse width modulation? Okay. Pulse width modulation is usually connected to which other part of hardware? With the timers, yes. So how do you generate pulse? What is pulse width modulation? Anybody knows that? Sure, but what is it used for? What is it used for? Pulse width modulation. Why do you want that?
When you drive something that wants an analog output, you can immediate digital, so you kind of just like burst full strength for a while.
You want to drive something analog, but you cannot produce an analog signal, so you want to produce something digital, and the phase of when this digital the amount of time which this digital signal is switched on, related to the amount of time which this digital system is switched off, gives you the energy which you actually provide to that device. What classical mechanical devices can you drive with that? LEDs, electrical motors, brushless or brushed electrical motors. And LEDs, what do you regulate with the LED with that kind of thing? The brightness, of course. Sure. That's an easy way, and with an LED you don't usually see this unless you use cameras which are fast enough to actually see the flickering in there. Hence, if you use high frame rate cameras, the technical world looks so weird these days because everything is flickering quite funnily and the brightness is not working anymore. Motors, yeah?
All those flicking stuff, is that easily fixed with a capacitor though?
Yes, that's what usually is. You don't have to do that because the human eye is not resolving that anyway. Yeah.
Isn't it like if you're applying a voltage to an LED, the light output is not proportional to the voltage?
Yeah.
And so you need to apply like the maximum voltage, and then you just regulate it on and off.
Yeah.
So you can't really use a capacitor to drive the voltage to half, so you might get much out.
Yeah. So they're reacting not very nicely. If you regulate the voltage linearly, they will just switch off at some point. And above that point, the brightness will only dim a little bit. So emulating this by regulating over time is actually a much more linear and controllable fashion. How about electrical motors? Can you run an electrical motor by just regulating the voltage which you give this motor? Will the RPMs be proportional to the voltage which you give to an electrical motor? Yeah? Yeah? Maybe? Actually, the same argument than for the LED, because there will be a low voltage at which the motor will just stop. Or worse, the other way around, it will not start. So it also comes with a very bad hysteresis in that case. With the LED, you don't have a hysteresis effect, but with an electrical motor, you do. Because if you have a motor still standing, and the brushes are in all kind of collections, and the magnets are in all kind of configurations at the moment, you need a certain voltage before that thing starts turning. Before that, you just have it doesn't actually do anything. Once you get above this voltage, and you have the first changeover to the next magnet, the thing all of a sudden goes heat. Now you regulate it down again, and calm down, right? That's very bad hysteresis effects which you have there. Now if you have a pulse width modulation, you don't have that. And you have the advantage that you always operate on maximum torque. Because you have maximum voltage always applied, if only for a short amount of time. But this maximum voltage translates into maximum torque and is independent of speed. Well, if you make it too slow, then it means that you're just making an electromotor sound like a diesel engine, because it just goes tok, 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 with every little pulse which you see there. And if you have the frequency too high, what happens then? You're just shattering the electromagnets into bits. Don't move either, so you have to have a nice compromise here to do that. So lots of applications for PWM signals. And yes, I don't think there is a single microcontroller which you can buy which is not able to produce a PWM signal. Can they also read in PWM signals? Why would that be useful? So to communicate with other microcontrollers? The other microcontrollers wants to control a motor, but you actually replace the motor with another microcontroller which actually interprets the signal then? Yeah, okay.
In a sense, can you treat the bit stream as a PWM signal, like the one we got through that last year?
Yes, you wouldn't actually use a PWM decoder for this one, but theoretically it has similarities to that, yeah. Okay.
We talked about ADCs.
Yeah, I was fascinated. Why do you guys are not putting ADCs in your microcontrollers? We spent a whole lecture about ADCs, and now you're not putting these things into your microcontrollers. Of course, you want to have at least a single ADC in that one, and possibly also a DAC, if you have the luxury of getting that one as well. So I think we are not too bad. A clock generator, so not the crystal, but the circuitry which is after the whole thing. Lots of interrupts, timers, lots of I/O, and these days you also have comparatively high-level I/O channels. But this is the bare basic. This is what pretty much every microcontroller has. In terms of CPU power, it's anything. You get 4-bit microcontrollers, you get very beefy 64-bit machines. As microcontrollers these days, there is no specific limit. Let me show you a microcontroller which you described for quite a while now. 68HC05, classical 8-bit little microcontroller, very old, and used in so many devices you can't imagine. Pretty much any kind of washing machine or devices like this which you have bought in the last 20 years will have something of that sort in it. At least have had something of that sort in it. What can it do? It has one 8-bit ADC, has one 16-bit timer, has 176 bytes of RAM. So note, this is not megabyte or gigabyte, this is byte. So you can welcome every instruction which you program individually by handshake in your system. Don't go object-oriented on that thing. It's not going to end nice. And you have EPROMs. So you can ask the guys which are programming, which are providing that for you, to either give you a possibility to burn that. Some of them have the possibility to actually program that manually, or you could ask the manufacturer to pre-program it for you. You give this program to the manufacturer and they burn it hard into the device with you being able to change that in post. What do you have? 2 megahertz, 176 bytes, a few power saving modes, a bit of serial connections, I/O bits, 3 times 8-bit parallel, 1 timer, 1 AD channel, 2 PWM generators. And this was the state of microcontrollers for decades. A number of variations. You could also buy them, of course, from other manufacturers, but this is what they mostly looked like. As you were quite limited in those kind of environments, no, these things were not programmed in Ada, but they were mostly programmed just bare in assembly. And classically, this is what it looks like to program these things in assembly, not even using any kind of an interrupt. Using busy waiting, polling. The very first instruction, branch until a certain output flag is being set to 0 or to a certain value. And you're just, the first instance is looping on the spot. And this is a classical pattern which you often see in these microcontrollers. They're not suspending themselves, there's no task switching, there's no context switching. You're actually staring at an I/O line until something is happening, and you're staring with the full might of your CPU at this I/O line until this thing changes. Brutal, very effective, easy to predict. You have a clear way to calculate how long that takes until this system will respond to any event from the outside. It cannot be more than a CPU cycle away from an actual response. Pretty fast. Fast with relation to a 2 megahertz CPU clock. And if you look at the actual chip, this is mostly, what do you see on this chip? What are the biggest components you could identify with the bare eye on that microcontroller die? Well, the pins, yes, of course, because somebody actually soldered wires on them, yeah? Okay. What other components with your 2300 or other hardware experience can you identify on the chip?
Registers.
Where are the registers?
On the left.
Yes, those are registers, these large banks on the left here. What other stuff can you identify? This whole area on the right is the arithmetical unit, which you mostly recognize by these long connections which are used for shifting effects, for shifting in the area. And most of that stuff is a bit hand wavy, so it's all hand designed, these chips. But most of the chip surface which you see is the actual CPU, with a bit of stuff around it, which has been squeezed into that one. Let's jump a few years ahead. That's an AVR32 microcontroller which is not that widely used, but the smaller brothers of this device are omnipresent. All the smaller 8-bit and 16-bit AVRs are everywhere. And if you look at those kind of breakouts, you will see that the actual CPU in this diagram here on the right, as well as on the block diagram on the left, the CPU is just a small thing which is in bold letters up there, and only a part of that is the actual CPU. The rest is all the memory around it. And you have many, many other devices around that one. And this is more what an actual microcontroller today actually looks like on the chip. We'll see actual chip photos of more modern microcontrollers later on. You see that the CPU becomes a smaller and smaller component of your microcontroller, which doesn't come very intuitively. Most people think it's basically a CPU which has other stuff around it. It's more a lot of stuff where accidentally you find a CPU somewhere in the middle of it, if you look at the chip these days. Detangling this diagram, that's a little bit of a different kind of specs which you find for this slightly more modern microcontroller. This is still a cheap end, simple microcontroller. 30-bit architecture, 66 megahertz, which is quite typical for microcontrollers. Microcontrollers are not clocked in the gigahertz range. They're usually clocked in around 100-ish megahertz range. A little bit more memory, lots of DMA buses. Power consumption becomes more and more important, so the power consumption is one of the most important factor being rated here. Nexus debug port, JPEG interfaces. Anybody knows what a Nexus debug port is? Talk about this in a moment. 113 GPIOs, standing short for general purpose I/O pins. You will play a lot with GPIOs later on, because ultimately everything you do inside of your chip has to be connected to one of your GPIOs. Hence these GPIOs today have to be so flexible, because you handle analog signals there, you handle different forms of electrical connections there. This can all be freely configured with the same set of IOs. Having GPIOs in the hundreds is quite standard these days. You actually have multiple hundred for more modern machines.
Would you use multiple cores, multiple processors on this chip, or would you even use an operating system?
Well, this one has only one CPU on it, but you also find microcontrollers which have multiple cores on them already. What you find is classically one or two ARM9 level processors on these embedded systems today. Running an operating system on that or not, I will defer that question. We'll decide that a bit later. You usually don't run, if you run an operating system, it's a real-time operating system for obvious reasons. So you usually classically don't run Windows on something like that. That defies the whole purpose of having this device in the first place. Whether you run it bare bone, whether you run it on a real-time operating system, that's up to you. You think at the moment probably in slightly larger systems, something like a Raspberry Pi, which is not really an embedded controller, not an embedded system. This is more of a miniaturized web server. And for these kind of devices, they are built from scratch with the whole purpose of running Linux on them, or any other operating system in a direct way. So they're all miniaturized, standard computers. Their real-time abilities are neglectable. They have barely any interrupt control and a few timers. Unfortunately, I was forced to research that in more depth than I wanted to, because when I was beginning to select hardware for this course here, of course, everybody's tempted, get yourself a Raspberry Pi for a few bucks. And it turns out that, yes, I can get this for a few bucks, but this kind of hardware does not lend itself at all to real-time processing in any sense. It has exactly one I/O line, which has been leading to a long fight in the Raspberry Pi development community, who is actually getting control over this one physical I/O line in the whole thing. Everybody else has to emulate. As far as I know, the fight was decided, I think, for the USB gang. So the USB interface on the Raspberry Pi has actually the only physical interrupt I/O line which this thing has. Okay. For a real-time course, it's not cutting it. So you need to have other hardware for that. Unfortunately, all the other hardware lend itself much better, and these days you can get, as we will see in a second, hardware which is much easier to handle here. Real-time counter, as opposed to an unreal-time counter. What is a real-time counter? 16-bit timers and a 32-bit real-time counter. What does that mean? Any imagination? Okay, come to that later, what that means. And directly an Ethernet controller, nice. Doesn't have an RJ45 plug, so you can directly connect into that one. But the controller hardware itself already part of the whole thing. For UARTs, anybody knows what a UART is? That's usually for universal serial communication. They're very flexible programming. Usually you call them USART these days because they're not necessarily asynchronous anymore. So it's universal series synchronized asynchronous. What does RT stand for? I don't know. I have to find out. And SPI interfaces, of course. 10-bit ADC could be a bit better resolved than 10-bit, but this is all what AVR gave you on that one. But therefore, you have actually 8 physical converters. That's not too bad. And bitstream output, sigma delta converter. This is your digital to digital converter, which I introduced in the context of sigma delta converters. Yes, you actually have digital to digital converters here to produce bitstream outputs. The AVR32 is quite frequently used in audio processing environments. So hence it needs that kind of bitstream interface anyway. Multiple cores. The Parallax, one of my favorite cheapskate multi-core machine. You want to show off with a 8-core CPU for $4, get yourself that thing. And it's quite beautifully designed. It doesn't have any interrupts. Why not? Exactly. Bring it on. We have so many CPUs. You can, if you want to actually handle a device on the outside, make one of your CPUs stare at this line. That's your interrupt controller. It's way more predictable than actually using an interrupt logic and interrupting your main program in 5 different levels and 5 priorities and hierarchies. You don't need to do that. You just have, well, I have enough cores. Just make one of these cores stare at this line. This is my implementation of this device controller. Right? Quite beautifully and clean design to do it like that. You have hardware semaphores on that thing. I don't think it costs $8 anymore, but it was costing $8 when I made this slide. Okay. So, and this is the toy which you will be playing with, the STM32F4 or F40. And same thing again. You have to start looking on this diagram to actually find the CPU. Found it? This small box on the top left, the fourth from the top, that's your Cortex M4. That's your actual CPU. And the space on the die is actually not unrelated to the size on this diagram here. The Cortex M4 is quite tiny compared to what else you have on this device. What else you have on this device? I mean, it's not proportional to the space here. Of course, the GPIO ports are not that large compared to the rest of the whole thing. But you have a lot of other interesting devices on that thing. We have 3 independent 12-bit ADCs on that one, and the temperature sensor is cleverly actually integrated into that block. It makes a lot of sense because you calibrate your ADCs and you calibrate this whole part of the very sensitive part of your device. You want to have good temperature measurement right there, which you get straight away. You have the USARTs there, lots of timers, I think 12 all up, no 14 timers you have all up. They're all different, they're all specialized for different purposes. Yes, there are some groups, usually they're coming in groups of 2 and 4, which can be used in an exchangeable way, but all of these timers can do, most of these timers can do quite different things as well. CAN-bus interfaces, I think there's some Ethernet ports, lots of DMAs. Yeah, there's an Ethernet port up there. Real-time clock. There's a random generator somewhere on this diagram. Yeah, on the top right, ING, that's a random generator. What's a random generator? As a block in hardware? Isn't that something you write in software?
It's kind of like saying those noise from the outside world and generate
It's plugged into the noise of the outside world. You think that thing has an antenna or something?
like the electricity is not always the same.
Building a random generator is a bit of an art form in itself. How would you build a random generator in VHDL? And can you just hold a wire in the air and say, this is my random generator? Which basically say that, well, it's probably receiving triple J at the moment, so it's random enough. Is that a quality measure for a random generator? You define it actually statistically. You have statistical quality measurement for how good is this random generator, and then the manufacturer gives you a guarantee it lives up to this and that standard without telling you what it does. So I can always imagine that a lot of the engineers got tasked to design an Ethernet port and design this and that, and occasionally you design stuff which just doesn't work. Right? Every time you try to do something with it, you produce random results. And so like trying to optimize your piezo crystals for being very, very temperature sensitive, a few of them are just black sheep and go the opposite direction. Maybe some of the device designs here just went the wrong way, and they say, okay, we can always use it as a random generator. I don't know. I'm sure there's lots of science in how this has been designed to get this right. Anyway, you do have a hardware random generator, which is actually of quite significantly higher quality than what you do with a pseudo random generator in software. Okay, what else do we have on that thing? We have voltage and current metering on the chip itself, so you can actually monitor the power consumption of that thing as well, if you like. The power dissipation is just 420 milliwatts, so barely half a watt if the whole thing is actually flawed, every device, all of the devices on that chip. This is like if you unroll all of these devices into a standard PC-sized shape. This is a pretty massive thing which you have at your hands here. And it goes down to just half a watt in power consumption overall. You can crank it up to 168 megahertz, which is, as I said, quite common in that range. You barely see microcontrollers which go beyond that, simply because power consumption goes quite exponential beyond that point. If you go to 500 megahertz and beyond, this will be a bit more problematic. The PowerPC community is usually going a bit further. Here you have the embedded PowerPCs. They're clocking a bit further because their power consumption has a very low starting point to start with. They have a good possibility to crank that up further. And the embedded PowerPC devices you often see in routers, in network devices, where you actually need the clock rate to keep the performance pumping here. What you have on that board is also an audio interface with a Class D speaker driver directly on the board itself. It means you can plug in a headphone directly. You have a USB on-the-go interface on that directly. Tons of watchdog timers, 2 32-bit timers, 16 DMA channels. 16 DMA channels, that's a lot of shuffling. You can do crisscross the whole device. What else is noteworthy? PLL, phase lock loop. Yeah, and you have actually 12-bit ADCs, 3 physical ADCs, and they can be multiplexed to 16 channels in total. Okay, you will learn lots more than you ever bargained to learn about this chip in the second half of the course. The reference manual, excluding the CPU, just the reference manual for the rest of the device is some 2,000 pages of quite beefy fine print information where every word counts, and many of us have actually read a good part of it to excruciating detail. Because you get a tiny bit wrong and the thing just stops. And it's very easy to crash it if you overlook a single instruction along the lines of this device interface is to be read in 16-bit instead of 8-bit. This has to be read in 32-bit, and you crash the bus and the thing crashes. That happens very, very quickly. Okay, another device. MPC 555 or 565. This is a PowerPC version. We use this one here for submersibles, for example. Very nifty little controller. Again, you see the actual PowerPC. It's on the lower left, the PowerPC core. That's the whole CPU. Look at the rest of the devices which I have scattered around that one. Of course, a megabyte of flash memory is already most of the chip. And the decoder logic, just for the memory, is much larger than the whole CPU. It's interesting. Left of the PowerPC core, you have the floating point unit. Floating point units are quite large in comparison. That's the reason why in early microcontrollers you never had a floating point unit. And these early microcontrollers were so slow that you weren't thinking about floating point processing to start with. But if you actually needed floating point processing, you need to go through a library. You need to actually emulate this in software, which I assure you everybody hated, because A, they were not working, and they were amazingly slow to do that. So we are all happy at the moment that every semi-upscaled microcontroller will come with a floating point unit on it as a hardware unit, which relieves you from a lot of trouble, because now you have your floating point operations at the CPU clock frequency, at least basic multiplication. And you also know that unless somebody messed up some tiny detail in the hardware controller, which is way more rare than messing something up in your floating point library, you don't have to worry about the precision and the dependability of that thing anymore. Beautiful. So what other things do I want to talk about here? Do we find... Oh, again, a Nexus debug port. Okay, I think we have to talk... Yeah?
What is it to
Canvas interfaces. They're all CAN bus controllers. I want to talk briefly about the Nexus debug port. This is a very interesting, nifty device. How did you, in the past, imagine how you would debug a device like this? A blinking LED and drink lots of tea and coffee to actually see the frequency. The classical debugging way, GDB, or whatever your favorite debugging environment is of course complete rubbish for those kind of environments, because if you use those kind of debuggers, you assume that you basically have a sequential system and it makes sense to actually stop it. Now, stopping the CPU here and everything else around is still running doesn't give you any sensible information. Plus, it is mostly used in a real-time environment, which means you cannot stop it in a sensible way. What have you done in the past to debug a system like this? How would you, from a hardware perspective, engineers to the front? Logic analyzer, yes, exactly. And it's a pretty beefy logic analyzer because you have a lot of pins on that thing. And this is pretty much what it looked like. They called it inline emulation, which means they ripped out the microcontroller out of its socket when these things were still having a socket. These days, of course, they aren't. But back then, there was still a socket on the microcontroller, like you have a socket on the main beefy CPU. So what you have done is you took a screwdriver, take the microcontroller out of it, and then put an in-between plug between your microcontroller and the board, where you have then all the wires hanging out of that one, which you hook up to some sort of a logic analyzer, which was able to analyze what is going on at all the I/O lines of your microcontroller in real time. Now, this was very messy because you have to actually physically access everything, and impressively expensive to do that, because those systems need to be faster than the microcontroller by definition, otherwise you can analyze what's going on in the microcontroller itself. And that was pushing the limits of what you could do at that time. Fortunately, there's some progress on the planet occasionally, and one of the most important progress steps here, besides having a floating point unit on the whole thing, is that the ability to look into your CPU is now integrated in pretty much all microcontrollers by default as an extra device, part of your microcontroller. This extra debugging device can do a number of things. It can actually look into your running, bleeding heart CPU. It can tell you the register values while this thing is running live with your SPI interface, with your Nexus debugging port, which pumps out this information as you requested while the CPU is actually running. So having a live view what is going on in your system is now almost for free, as long as you have a device which can hook up to this standardized debugging port. Cool, huh? Instead of ripping this whole thing open and have a gigantic logic analyzer plugged into the whole thing, you only need to have something which is fast enough to run this serial communication to the whole thing. And you can have CPUs which are fast enough to do that because they're not clocked at gigahertz, they're clocked at a few hundred megahertz. So you need to have something which can interpret it on the other side fast enough. You can also change register values. You can get information when a specific memory address has been triggered, for example. You set traps into this debugging environments, just like you used to in a GDB environment, only that this thing is actually running live at the same time, which is pretty cool. So this was a big progress step for microcontrollers. Okay. Time processing units. What could that possibly be? Fancy name. A processing time. Give me some time, I process it. If you look at the diagrams here, where the time processing units are reasonably large-sized devices here. The time processing units are almost the size of the whole floating point unit. If I take 3 of these time processing units together, I almost have the size of the whole CPU. So So they must be doing something interesting. This is taking the concept of having lots of concurrent entities in your controller to the next level, so to speak. Those are small CPUs which are dedicated for specific hard real-time applications, and they're running completely independent of your main CPU. You can task them to do specific time-oriented, hence time processing unit, jobs on the I/O lines, which you would need to otherwise do it through your main CPU, and multiplex your main CPU with interrupt controllers to handle multiple I/O lines. Here you have 3 time processing units which can do that for you. And they're pretty serious about the real-time aspect of these time processing units, which means that these time processing units communicate with your main CPU. How? How do you communicate with another CPU without ever disturbing it? Shared memory? How shared memory? You have shared memory, okay. But shared memory means you need to synchronize your shared memory, right? Mutual exclusion.
Is there like a register that represents?
They have registers?
There's one register that you read from and just represents.
Okay. But still you have this problem of if they're both reading or writing, how do you handle that? Interrupt is not. Interrupt is disturbing the other entity, right? You're interrupting it. You don't want to do that. You want to actually leave those units running completely undisturbed. You want to exchange data with it while it is running, without ever disturbing its pace, which is going. So memory-based synchronization is a good start. I'll give you another keyword for that. It's not a random form of memory, it's a dual-ported RAM. Have you ever heard of a dual-ported RAM? What could that mean? Well, 2 ports. Okay. That means physically something very simple. You overclock your RAM by factor 2, and you alternate the access to these RAM, to these modules between 2 different devices. This is what physically means dual ported. So that you can read and write from this RAM area without anybody ever noticing any interference with somebody else. So they can both read, they can both write, but they're actually multiplexing. So the RAM is only listening for half of the time to one device, half of the time to the other device, but it's running so fast that both devices think they're running at full speed. Clever, huh? And this is the way how you interface the main CPU with these devices via dual-ported RAM modules, which are twice overclocked, to provide this kind of complete independence in terms of free-running real-time devices. And this gives you an idea how serious people are working on these real-time devices, that they're going through this length to guarantee that you will actually have free-running real-time devices which cannot physically be disturbed. You have no way to get this out of whack by whatever you do on interfacing with these devices. Okay. Closer look at these time processing units. This is one of the 3 time processing units. It's an independent micro engine, so it has micro instructions. You can program them with these micro instructions. It's not a PowerPC. It's a much more primitive CPU. It's not a universal CPU. No, actually, it's a Turing complete machine. It's a Turing complete machine, but it's much more primitive than what you would have on a PowerPC. It has a hardware scheduler. That's interesting. So you don't have to write your scheduler in hardware, in software. you have a schedule already provided for you. In fact, you have 3 schedulers because you have 3 real-time processing units in hardware already provided for you. And they can work on 16 channels per time processing unit, and there are 2 time units which are dedicated and only accessible for the TPUs, not from the main CPU, exclusively used for those. Okay. Predefined functions. This is your request fulfilled. You said, I want to have software which works already on the whole thing. And these time processing units come with a whole bunch of programs already burned into the device, which you can just call and select. I want to have my time processing unit to do that. Because, well, the guys who actually designed that probably know how to program that thing. And they programmed it already so that some of these functions which you frequently use are already available straight out. For example, controlling a stepper motor or decoding a quadruple input signal, synchronized pulse width modulation. If you have a large plant and you have a lot of motors and you need to synchronize the pulse width modulation for all of these motors in a sensible way. Otherwise, your lights begin to wobble with the frequency of your motors, because if you actually pulse them all at the same time, this is like having your switch mode power supplies at home all synchronized, and you probably will get the whole suburb out of whack if all of a sudden all your switch mode power supplies are beginning to synchronize with each other and getting the phase of the mains shifted slowly that way. In a larger environment, if you have actually beefy electrical motors there, that becomes an obviously even more urgent issue. So you need to coordinate these kind of things. Measuring periods, measuring pulse width, PWM signals which are coming from the outside as well. This is what you can use predefined. We are computer scientists, right? We don't want to use predefined stuff, we want to program ourselves. What can we program in there? You just switch off the RAM module and program this thing manually. We can have 16 different functions in total, which this thing can fulfill. And 32-bit wide micro instructions. That sounds scary. Good news is, this thing has exactly 5 instructions. The bad news is, they're damn complex. Because as often in these microcontroller environments, if you program with instructions directly on these controllers, a lot of CPU parts are programmed at the same time. Actually, this is also how a lot of CPUs are programmed internally, not on the machine level, which you see from the outside, but internally, this is often decoded in much, much longer instructions. And each bit of these longer instructions will trigger action in your CPU, in multiple parts of your CPU at the same time. Now you do this by hand. You can do this by hand if you really want to. 5 different instructions, and I colored it in for you a little bit, in 4 different groups. Execution unit, that means your ALU, your arithmetic logic unit, which is part of the time processing unit. It's triggered by that. Channel control, which means you can control the signals to the outside. You can latch signals in, which are coming from the outside. Access to RAM and sequencer information. And the sequencer information is complete enough that you do actually get a Turing complete machine in the end.
What's the benefit of having this with having 8-bit instructions and 16-bit instructions and more?
8-bit instructions and more of them. You're losing a lot of performance because you can now only do this sequentially. If I break this down into little 8-bit instructions, then I have an instruction which does a sequence operation, a jump. I have an instruction which does adding 2 numbers. I have an instruction which loads data from memory. And this is how you think as a programmer. You actually do this sequentially.
There's real time
But this is not what a CPU does.
So performance didn't really matter in real time.
Yeah, okay, point taken. You can think of it like that. These guys thought that we are brave enough to handle those kind of interfaces as well, because you're not losing any real-time performance here, or any real-time control that way. You just gain more possibilities to do things concurrently. And what CPUs are actually doing internally is, of course, that the sequencer is running, of course, at the same time as the RAM module, at the same time as the arithmetic logic unit. This is not done in sequence ever, right? Even though it looks like that from your programmer's perspective. Here you do it explicitly, concurrently. Unrolling the individual instructions. The first one is a combination of execution. All this pinkish stuff here is arithmetic logic unit. And RAM access. The instruction at the very end is a decrementer or end control information for the sequencer. I have a number of different possibilities. You can have set this to nothing, which means that it just executes the next instruction after that. You can set it to end, which means your function actually stops there. Well, I have to understand what that means in a moment. And you have a decrementer, which means you can say that this instruction is supposed to be executed until this value is 0. So you can have immediately a repeat instruction for the sequencer in this instruction itself. So this can loop 5 times just by setting the decrementer accordingly, and then you can point to the right address. Next instruction is a combination of, again, execution units, a bit of channel control. Ultimately, you want to have interaction with the outside world. Finally, we get to a bit more computer science instructions. Here you have branch control and conditional branch possibilities. Conditional jumps, far jumps, and again, decrementer at the same time as you can control your I/O channels a little bit. At the same time, you can load data from the outside. So all 5 instructions do everything at the same time, but a different emphasis. So some do a bit more RAM, some do a bit more of this. And the last instruction is more execution heavy, and execution heavy combined with channel control. Let's have a look at an actual atomic operation here. This is what one of these functions would look like. And never mind what arithmetic this thing does or what I/O channels are being triggered by the whole thing. Just check out what the sequencer information here is. You have the first one is set to nothing, which means just goes to the next instruction. The next one is a decrementer, which checks a specific register and counts it down to 0, and only proceeds if this one is to 0. And here you can also count down to 0 in the second to last instruction, then call a function at a specific address once you actually get there, and then you have an end state. The point of the end state is, so to speak, the yield operation which I have in this CPU. You have a number of different operations at the same time on different priorities, and at each end state you give the scheduler the possibility to change processes, to change to a different function. If you don't do that, everything before that is atomic. It's quite interesting. It's a low-level machine language where you define directly the atomicity of your system. You cannot be interrupted before you actually say end yield, and then the next function can come, the next operation can come, the next atomic operation can come. But you have a guarantee of being atomic, uninterruptible, inside each of these functions. You cannot do this on the main CPU, right? As you all know. If you're lucky, you get information on your main CPU that something interfered with me, but you usually cannot just declare a block of instructions on your CPU as this is supposed to be atomic from here on out. You always have to consider the possibility that somebody presses an interrupt. Maybe a non-maskable interrupt, you cannot avoid it. Here you have this possibility to say those parts will be atomic. Interesting. Okay, next step. Now we have non-interruptible microcode blocks. Those are called states. Out of these states, I can build whole functions. And the last thing to do, I just have to associate these functions now with I/O channels and with the time bases I have available. I have only 2 time bases, so I cannot be too generous with the time bases and the functions. And I let go. And I have a system which handles my I/O here and gives me information on the other end in the dual-ported RAM to my CPU at the same time. And this can be calculated down to the last CPU cycle, how long that takes. Before I do that,
Is there a compiler for that instruction set?
there is a development environment for that, It's not that you get a C to time processing unit compiler, but there is an environment which helps you with that. But it's more of a macro assembly environment, obviously. But before we can calculate how long things now take, down to individual clock cycles, we need to understand an important module of this time processing unit, namely the scheduler. The scheduler is a bit of a weird one. It's a round-robin scheduler, which is very weird for a time processing unit, for a real-time environment. A round-robin scheduler with priorities. So it's a weird crossover between what you will find in a Linux environment and what you will find in a hard real-time environment. Because you will not have in a real-time operating system any kind of a round-robin thing. But here you have a round-robin which is connected to specific priorities. So you can place your functions in different priority bands. And depending on the priority band, you will get access to the CPU in a certain pattern. And the priorities here simply mean that on the highest priority, you will get access to the CPU every second time. The next lower priority, a little less frequent. I'm not saying every 4th time because it's not right. It's a bit of a more weird pattern which is actually on the screen here. And the frequency goes further down if you go on the lower priority. Okay, but you know that this scheduler is hardwired to do that for you. You cannot influence that. If you have unused slots, they're automatically propagated to the next priority. Okay, we have to know and define that as well. Now, this picture here is, of course, not the real thing, because your states which you schedule, the individual blocks here are the states which are uninterruptible, but these states are not the same length. So first you have to actually calculate the length of these states, but that's not too hard because you can actually count them. At least unless you went not too haywire with your programming. If you restrict it, and it's a Turing complete machine, so yes, you cannot calculate in all circumstances. But what you will do here is mostly not classical Turing complete programming, but you have much more simplistic programs where you can calculate that. Okay. What do I need to consider to calculate the overall latencies now? Clock frequencies. What is the time base of my timer there? I need to count the microcycles for each individual state. I need to know the amounts of RAM access, because the RAM access will give you a little delay in the whole process. You have an extra cycle per RAM access. The RAM access is Same as what you, by the way, had in ARM programming in the past. If you have done that, rmxs is just half the speed of normal one in the embedded world. And for every state switch, you also need to add 2 microcycles. So we're getting a little closer. Emulating the execution times for all of these states, then adding the changes to that one, adding the amount of memory access which you know will happen to the whole thing. And in order to calculate the latencies for individual functions in your microcontroller, you do something which you will later on do also in your real-time scheduling analysis. You assume that all states on the same priority are runnable at all times and at maximum length. So your bodies on the same priority level will try to delay you maximally by being on their lowest speed, and they always only execute at their lowest speed. Assume that the longest state out of all higher priorities are running at all times, so only one state on the higher priority you have to consider to calculate the maximum latency. Makes sense, because this one state can interrupt you every time. And similar for the lowest priority. And then you have to calculate that for the full hypercycle, and that gives you the maximum latency for this highest priority task, which looks like that, for the medium priority task, which looks like that, or the lowest priority task, which looks like that. For the lowest priority task, I just have to figure out one state from any of the higher priority bands, which is the longest state I can find anywhere in any of the higher priority bands, and I assume this is always runnable. This gives me the maximum latency. And people do that. So this is a classical form of analysis which you do step by step and calculate the overall latencies of your system. Of course, you can make your life a lot easier by not having any other functions on the system to start with. You have only one function there, that makes your life a lot easier. And many of the TPU programs are actually like that. You don't have 20 different functions on the same TPU to begin with. Cool. Real-time clock. 64-bit real-time time base. Free running. That's the definition of your real-time time base. Free running. How free is that? It's so free that you can do whatever you want with your device. You can program as hard as you want to try to influence that one. It will not budge. It will not move. It will not even respond to a reset. It's free running, and that gives you the hardware guarantee that you can depend on this counter as a reference for your real-time environment. This is your generated real-time on your chip, because you have a guarantee, no interrupt, no software instruction in your CPU will ever touch that thing. Interesting. 64-bit, clocked at 20 megahertz. That gives you about 30,000 years before that thing runs over. Should be fair enough. What's the usually required time that you have to guarantee a device is able to stay online, stay up in the real-time embedded world? Probably not 30,000 years. A bit more realistic. What uptimes do you want to guarantee for your machine? What is your uptime, your guaranteed uptime of your laptop? 2 minutes? A day? A week?
Depends so much on the task. Like if you know there's a definition that's going to take 4 years,
Yeah. If you want to sell a device for a high integrity, safety critical environment, you usually assume that all the time bases have been set in a way that it runs without running over and producing any weird overflow effects for about 50 years. So at the moment, nobody assumes that we will have devices at all which are able to run for more than 50 years without having a power interruption. But that means 50 years without ever having a low battery or somebody ripped out the power cord because you need to plug in the vacuum cleaner or something like that. Yeah.
So when you reset the start from zero again, like
if you pull the power, yes. But you have to physically pull the power. Of course, the timer does not keep running when you actually remove power. But that's the only thing to stop it. Pressing hard reset on those devices will not influence the timer. All right. So 64-bit is, I think, plenty for those kind of environments. And you also have a real-time clock. We'll talk about this a little bit in way more detail in a later chapter in the course, but just foreshadowing it a little bit. What is a real-time clock? It has real time. Okay, besides me pronouncing it funny, what's the semantic of that? It's real, man.
actual time of day.
Actual time. What's the actual time of the day? How do you measure that? You need some sort of reference. Well, that's cheating now. You're just saying you ask somebody else. Right? So this is more of a communication interface. You ask somebody else what the time is.
Because it's so accurate, you always have to take your own reference. Because so you can't where your gravity and your speed and you can't guess it in relation to other people. It's your time. It's personal.
Yeah. Okay, what's the definition of real time from the perspective of you as a programmer? In which way can real time change? You said you have to communicate and synchronize with the rest of the world to find out what real time is, right? You cannot just define real time on your own. Okay, so what if you ask me what time it is and I tell you something now? You take this time and you take your own time. You ask me in an hour again, and I tell you what? Exactly what you measured? Something different. Different how? Will I always be slower than you? Always be faster than you? You don't know, right? Well, that sounds dangerous. Because I tell you that you have to jump into the future, that your clock was too slow, just add another second to your clock to catch up with the world. This is probably harmless. You lost a beat, you jumped into the future. But if I tell you the other way, if I tell you, you're too fast, I have to reset you into the past. That's semantically weird. Your programs now live through the same time again, because I just reset you to an earlier time. How do you handle this logically?
Why would you want to do that? Unless you're a genius.
That's the definition of real time.
There's no such thing as real time. That's a fallacious concept. Also, is it real time on Mars the same as real time on Earth? No, obviously not. Right?
No, real time is defined. Okay, we have to define what real time is first. Why do you say you have to synchronize with somebody? Why don't you say you make your own real time?
Because what's the point if you use real time to coordinate with
Okay.
another system? So
What is dictating what we think is real time?
the
The government. No, it's not actually the government. Who is controlling that? Any idea?
Standard bodies.
Some standard bodies? Committee. committee of old men sitting somewhere. They tell you what real time is. But what are they talking about? What are they negotiating when they define what real time is?
Atomic reference.
They're taking an atomic reference.
We
Okay.
talked about this in 2015.
A little bit, yeah. An atomic reference. So yes, usually you have an atomic clock somewhere. But it's much simpler. How do you know when it's 12 o'clock?
Sounds straight up.
Exactly. That's the definition of real time. That you know where the sun is. Because our definition of real time is simply defined by night and day. That's our definition of real time. And if you want to synchronize with the rest of the planet, you better agree with these other guys where the sun is. But that's hard to agree precisely. Because I have to tell you something ugly. The Earth is slowing down. Not very fast, but noticeably enough that time is actually changing in that sense. And we don't know exactly how fast, so we have to add a little bit of time here and there and adjust that a little bit to agree on that one. Now, from the perspective of your local device, working with real time means that you have to prepare yourself to be corrected in both directions. Yeah.
I think you guarantee it's slower than you only ever have to move forward.
Yes. And that's not called real time, that's called monotonic time. That you still assume that I can be corrected, but I can only be corrected forward. So my time will always monotonically increase, and I can still try to synchronize with the rest of the world, and I purposefully slow myself down, so that I know I'm too slow, so occasionally I have to synchronize forward. That's called monotonic time. Ada gives you both of these times. You have the calendar time, that's real time. Calendar time, as the name suggests, that has something to do with the sun. And calendar time doesn't give you any guarantee in terms of whether it's corrected forward or backwards. And you have monotonic time. Monotonic time can also be related to what has happened outside, but it only ever goes forward, which makes your real-time designs a lot easier. I get to that one? Because we defined real-time clocks and free-running clocks, which are exactly defining these kind of things in hardware for you on your devices. Right. Yeah.
Unless we get to the point where we need to eventually interact with the outside world in the state that we have to turn all the lights off at 6 p.m. or whatever,
Yeah.
why do we have to care about the slowing down of the Earth? Just live in your own little massive counter world and don't worry about this stuff.
Yeah. This is one of the first questions which are actually asked if you design a real-time system. What is actually my real time? Can I generate my time myself and call this as my real time? Or do I have to synchronize and communicate with the rest of the world? Do I have to agree maybe with a bunch of other controllers around me about this time? Or do I have to agree with some time committees someplace what the time is? And the design of your real-time system depends to a certain degree on those decisions which you make early on. So your question is perfectly right. You have to be very conscious about what is my definition of time, where do I get my time source from. Okay, we talk more about what time means and the philosophy behind that, the physics behind that. We need to have a very clear understanding what time means before we define and program in time. And you have all the technical background and possibilities to do that. All right. Any further comments, questions? You want to get something to eat eventually. Okay, enjoy your dinner. See you. Thanks.